5.3, number 196. We're supposed to evaluate the integral from 0 to pi of magnitude cos t. Okay. It's an interesting little problem. And all of these that have magnitudes on them have a special methodology for evaluating them, which I'll show momentarily. I just want to give an idea of what's going on with this particular example with a picture very quickly. The picture is not going to be too precise. The goal is just conceptualization, not accuracy here for the moment. So cos t, forget the magnitude for one moment. Cos t from 0 to pi. Let's just call this pi on 2, and this is pi here. Okay. There's 0, and we'll call this 1, and down here is -1. So then cos, we know, starts at its peak, and also its y-intercept here conceptually, and goes down to a 0 value at pi on 2, and then continues downwards towards a low point, towards a relative minimum of -1. Right? And it keeps going forever in this manner, and so forth. I'm not worried about the rest per se, because we're just evaluating what's going on between 0 and pi for our integral. But just to continue a little bit here. Okay, so there we go. So we are looking at from 0 to pi in particular, and if we were to start to color in the area that we're finding, again, ignoring the magnitude for a moment, just for a quick moment, ignoring the magnitude. There is, without the magnitude, this would be the integral of cos t dt from 0 to pi. The blue area, right, is what that would be. Now, we know the integral calculates net area. So here, this sector and this sector would exactly cancel each other. They're the exact same shape, but one's below the x-axis, so this is negative, and one's above, so this is positive. Okay? So therefore, this answer is actually 0. So what's the difference between this and the other one? Well, the magnitude does something to this area down here. It actually flips. Anything that's below the x-axis, the magnitude function is going to flip that part and make it occur above the x-axis. So this would really be up here now. And so the cosine with a magnitude on it would look like a bunch of peaks, right, just jumping across here like this. It would look like this, okay? Over and over again. Nothing below anymore. Right, so that's magnitude of cos t. That's what it would look like. So that means is the area has shifted to being above. So now it's just really doubling the first area. Now, not all problems double, right? Not all problems are as symmetric as this one. But the idea is that all the areas that were below, the magnitude function is forcing them to be above now, because that's what it does. It makes negative things positive. Okay? So what we need to find here, it turns out, is this location. Where the function goes across the x-axis, where it goes from positive to negative or negative to positive, is what we need to figure out here, because that's where the magnitude function starts doing its job in a sense, when the function turns negative. Right? So within our interval of integration, 0 to pi, we need to figure out when does cos go negative. So it happens right at pi on 2, right? That's where it starts to switch from positive to negative. So we want to split this up. 0 to pi on 2 pi on 2 to pi. All right, so that's what we're trying to do. And if there were more places where it changed sign, I would have to find those roots as well. This one only has 1 between 0 and pi, our logarithms of integration. So the breakdown here is at pi on 2. So we use that property that we mentioned before, that you can always split up an integral along its interval at any point in between, and actually outside of the interval as well, but this one happens to be in between. So pi on 2 is our split. Now from 0 to pi on 2, cos is positive. So therefore the absolute value does nothing to it. And this is how we're going to get around taking antiderivatives of a magnitude, because we don't have a rule for that. That's why we're playing this game here and using this method to split the integral into two pieces or more, depending on the problem, so that we can now eliminate the magnitude symbol, because from 0 to pi again, 0 to pi on 2 again, cos is always positive, so therefore the magnitude function does nothing to an already positive set of positive cos values, right? This stated exactly how it was. So we have cos t dt. But now over here, we're adding the next integral from pi on 2 to pi, but cos here would be negative normally. So therefore the magnitude function is doing something to those negative values. It's negating them and making them become positive up here. So therefore I can replace the magnitude function with the negation function. I can negate cos t. That's all the magnitude function is doing to this function, as long as I'm on the interval pi on 2 to pi. All right? So now we've eliminated the magnitude function, which we don't have to anti-differentiate directly because there's no rule for that. This is how you deal with it. And now we can use our regular antiderivative rules and fundamental theorem of calculus part 2 to evaluate both of these. So over here we know the antiderivative of cos is sine, so we get sine t evaluated 0 pi on 2. And I'm going to take this minus to the outside, minus cos t again will be sine t evaluated pi on 2 to pi. Now, although this is just a straight calculation now, if we just think about it for a brief moment, what should happen, according to my picture here, is that when we get the first integral from 0 to pi on 2, right, the first one we calculated here, whatever that number is, basically we should just be doubling it. Now again, that's not how it works for every single problem. It's only because of the extensive symmetry of the cosine function that we have that happening, and because of the particular limits of integration that was chosen for this problem. But just for this one alone, let's think about it for a quick second. We should just take this value, whatever this number is, that's the area here, and we should just multiply it by 2 to get the area here combined with it. And we'll see that pan out as we finish the problem, hopefully. So here we have sine t, so we have sine of pi on 2 minus sine of 0. Okay, so that's the first one, minus the same basic thing with different limits of integration. We'll have sine pi minus sine pi on 2. So look what happens. Sine pi on 2 is 1, so sine 0 is 0. Sine of pi is 0, and sine of pi on 2 is back to 1 again. So we have 1 minus negative 1. Right? Again, this 1 is the first red area. This negative 1 is the blue area, and we have negated it, right, through this process. I mean, we're not doing it here at the end informally. I'm saying it's happened here as we thought about the problem appropriately with what the magnitude function was doing to this part of the integrand. But anyway, so 1 here, negative 1 here, and because we worked it properly, this negative is going to compensate and shift this negative area into a positive area, which is exactly the same size, right, same magnitude, 1, as the original red area here. So therefore we get the answer of 2.